Okay, so we understand that electrons have certain energy levels that are allowed to them. And the main energy level is the principal quantum number 1, 2, 3, 4. Within these main energy levels are subcategories. The next subcategory is known as a subshell, S, P, D, or F. And within these subshells, we have orbitals that have a specific shape based on the subshell. So S sphere, P peanut, D double peanut, and F flower. Now, what is the difference between a 1s subshell and a 2s subshell? The 1s, because it's in the first energy level, is closer to the nucleus, and the nucleus is going to be at the center of this Cartesian coordinate system. The 2s also has the spherical shape, however, it's going to be farther from the nucleus. So when we're talking about subshells, we typically indicate the energy level that subshell is in with a number right in front of it. So 1s tells me it's in the first energy level, S tells me the subshell and the shape of the orbital. 2s tells me second energy level, tells me the subshell and the shape of the orbital, and I know that my 2s is higher in energy, so it's further away from the nucleus and therefore a larger shape. Now, if we were to look at a probability map, what it would look like would be these little dots, which is often referred to as a cloud. And these dots indicate probability where an electron can be. But for convenience sake, we typically just draw it as this solid figure, even though we know that it's not exactly necessarily in this place. It's just 90 to 95% probability that electrons will be within this given shape if they're in a 1s or a 2s subshell. So let's look at more detail at the p orbitals in the p subshell. Here is the probability distribution. Here it is drawn more simply. They all have this peanut shape, and the difference between the three p orbitals is merely their orientation with respect to the nucleus. Our nucleus is at the center, and we call this the px orbital because it's on the x-axis, the py 90 degrees apart, and the pz. In chemistry land, our z is always the up and down axis, although I think in math many times the y is. But in chemistry it's always going to be the z that is up and down. And then here we see our d orbitals. There are always 5 d orbitals, and here are the probability distributions, this cloud-like formation, and here's the more simply drawn shapes. We see 4 of them have the same shape, and the only thing that is different is their orientation around our nucleus. So the dyz is between the y and the z axis. The dxz is between the the dxy is between the x and the y axis. The dxz is between the x and the z axis, and the dx squared minus y squared is on the x and the y axis. So you see these 3 are 90 degrees apart, and this is 45 degrees apart from this one right here. These are in between the axis, and these are on the axis. And then here's our funny shaped one, our dz squared on the z-axis. Looks like a p orbital with a donut around it. Now, in a hydrogen atom, which only has 1 electron, the subshells in a given shell all have the same energy. If we're looking at a hydrogen atom, the S and the P both have the same energy. The third energy level of a hydrogen atom, S, P, D, all have the same energy. The fourth energy level of a hydrogen atom, S, P, D, and F, all have the same energy level. However, if we're looking at any other atom with more than 1 electron, any other atom, these have slightly different energy levels. So if we're looking at any atom except for hydrogen, the S orbital will always be lower in energy than the P. So here in our second energy level, the S orbital has slightly less, or the S subshell has slightly less energy than the P subshell. In the third energy level, the S subshell has less energy than the P, the 3P has less energy than the 3D. And then in the fourth subshell, the 4S has less energy than the 4P has less energy than the 4D, and the 4d has less energy than the 4f. So within any other atom except for hydrogen, we can rank these orbitals in a given energy level according to their energies. And so to simplify it, S is always less than P, is always less than D, is always less than F in a given energy level. We can only compare these for a given energy level. So we're looking at, since we have all four here, this would have to be the fourth energy level. 4s less than 4p less than 4d less than 4f. And as we saw in our other representation, the s subshells always have one orbital, p subshells always have 3 orbitals, d subshells always have 5 orbitals, and the f subshells always have 7 orbitals. And again, here's that graphic again: s subshell, p subshell, d subshell, f subshell. And within each subshell are orbitals: 7 orbitals, 5 orbitals, 3 orbitals, 1 orbital. Now, as in the Bohr model, atoms can gain or lose electrons as energy in the atom go between different orbitals in different energy shells and subshells. We also refer to the lowest energy state as the ground state and any higher energy states as excited states. And as in the hydrogen atom, when an electron absorbs energy, it will be an excited state, and then it will always release that energy to go back to the ground state. And the energy that it absorbs and releases will be in the form of photons of electromagnetic radiation. So looking at the historical understanding of the atom and the electron, both Bohr and the quantum mechanical model, which was developed by Schrödinger, predict the spectrum of hydrogen very accurately. But the Bohr model stops at hydrogen. After that, only the quantum mechanical model, based on statistics and wave functions, predict the spectrum of multi-electron atoms. So this is what we use primarily, although we do give credit to Bohr and we can use it for any hydrogen atom transition. For any other element, we've got to use our quantum mechanical model, which makes uses of our quantum numbers, subshells, and orbitals.